So up until now, we have been counting the possible arrangements of different objects using permutations. And using permutations led us into using factorials, because factorials were sort of an easier way of calculating these permutations. As we were doing our permutations, the one thing that was always the same about the sets of objects that we were arranging was that all of the objects in the set were unique or distinguishable from each other. So for instance, if we go back to our old sock drawer question here, we have been working with socks that are all completely different. Okay? So imagine your sock drawer consisted of just single socks that were all different. You would have no trouble using a permutation to figure out how many ways that you could arrange these socks. Or to put it more mathematically, if you've got a set like 1, 2, 3, each of the elements in this set are distinguishable. Okay? In real life, our sock drawer looks more like this. We've got a bunch of white socks, a bunch of blue socks, a bunch of red socks. You can't tell these socks from one another. In particular, you can't really tell, socks come in pairs, you can't tell the left sock from the right sock most of the time. So these socks are what we call indistinguishable. Or numerically, we could have a set that consists of some numbers that are repeated a certain number of times. How many ways can we arrange the things that we have in these sets where items in the set are indistinguishable? Well, what we're going to do is first we are going to remind ourselves how we can arrange things when they are distinguishable. So let's imagine we have 4 socks, 2 blue, 2 red, and for some reason we've labeled them left and right. So once we label each one of these left and right, we know exactly which sock is which, and these socks are now distinguishable. So if we have 4 distinguishable socks, how can we arrange, or how can we do a permutation of these 4 objects? Well, the permutation, we've got 4 things, we're taking 4 of them out, so the permutation is just going to be 4, 4. Okay? And we know from our work with factorial notation that this is going to be 4 factorial, or 4 times 3 times 2 times 1. So there are 24 ways that we could arrange those 4 socks that we have right there. Now, what if these socks aren't labeled left and right? We've got 2 reds, 2 blues, and the 2 blues are indistinguishable, and the 2 reds are indistinguishable. How many ways can we arrange them now? Well, we can actually try making all of the possible arrangements. We can go red, red, blue, blue, red, blue, red, blue, red, blue, blue, red, blue, red, red, blue, and so on and so on and so on. And we would see that there are only 6 ways that we can arrange these 4 socks if 2 of them are indistinguishable. And this makes sense that it's a smaller number of ways, because if I look at this first one here, red, red, blue, blue, I can rearrange the red and the red, but that's not going to make any difference, because I could swap them, but I can't tell that I've swapped them because the 2 red socks are identical, are indistinguishable. So there are fewer things that we have to rearrange that we can tell that we have created a different set. We want to know a way of calculating this number of ways without having to write out the possible sets every single time. So the way we do this is we start by thinking about, let's say we've got these 2 blue socks in our set here, our sets of things that are indistinguishable. Okay? How many ways can we arrange these 2 blue socks? Well, if we're doing 2 socks, taking 2 of them, thinking of how many ways we can arrange them, the permutation is just 2, 2. Okay? So that would be 2 factorial. How many ways could we arrange our 2 red socks if they were distinguishable? They're not, but what if they were? How many ways could we arrange them? Well, it's the same permutation, p 2, 2, or 2 factorial. So to calculate the number of arrangements of our 4 socks, okay, with 2 blue ones and 2 red ones that are indistinguishable, this is what we do. We start with the number of arrangements if they were indistinguishable. If they were distinguishable, sorry. And I know I'm going to misspell distinguishable. So, if they were all distinguishable, we could arrange them 4 factorial ways. Okay, that was the first question that we did up at the top. We know that the fact that some of them are indistinguishable is going to reduce the number of arrangements that are possible. So we sort of have to divide out these cases that aren't really new arrangements because the socks are indistinguishable. So we've got 2 red socks that we can arrange 2 factorial ways, and we've got 2 blue socks that we can arrange 2 factorial ways. Okay. So this is sort of, we're canceling out the fact that the blue and the red are indistinguishable, or sort of cancel out the indistinguishable arrangements. Now, what do we get when we do this? Well, 4 factorial we know is 24. 2 factorial is 2. 2 factorial is 2. 24 divided by 2 gives us 6. Okay, which is what we expect because we actually figured it out by writing out all the possible sets. Okay? So let's look at a couple of examples where we apply sort of this formula here. How many ways can you arrange the letters in each word? We'll start with this first one, this 4-letter word here, seam. Okay? And we'll start by just counting how many letters we have. We have 4 letters. How many of them are identical or indistinguishable? Well, we've got 2 E's. So we'll just say we've got 2 E's. So our number of arrangements, I'll say n, is going to be the number of ways that we could arrange 4 letters if they were all different, 4 factorial, and divide out the fact that 2 of them are identical or indistinguishable. 4 factorial divided by 2 factorial. We know that 4 factorial is going to be 24 again, divided by 2. So there are 12 possible arrangements. A slightly longer word here. We've got sassafras. How many letters do we have? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. How many of them are the same? Well, let's see. We've got 1, 2, 3, 4 S's. We've got, let's switch colors here, 1, 2, 3 A's. Do I have any other letters that are the same? Nope, all that's left is F and R, okay, and those are different. So, how many ways can we rearrange these letters? Well, if we've got 9 letters and they were all different, we could arrange them 9 factorial ways. And now we want to cancel out the fact that we've got 4 S's and 4 A's and 3 A's that we can't tell apart. So divide that by 4 factorial and by 3 factorial. And then we just punch this into our calculator and it'll tell us that there are 2,520 ways of arranging them.